And so on this page, Alright, any more need to get stapled or passed back? Over? In? You got them. Notes open. Here's what we're doing today. We started section 2.6 yesterday. We're going to try and finish him today. I introduced things like vertical asymptotes, horizontal ones, poles. We're going to talk about slanty asymptotes today. It's kind of funny. They're called obliques. We can call them slanty ones. And then we'll see if we can be amazing and end up being able to graph a nasty rational function for the most part without a calculator. Okay, so behavior is where we ended. We had just started this section. There were tons of questions on 2.5. Remember? It was a rough one. Got people up to the boards, all that jazz. But we were able to get into section 2.6, rational function ratios of two functions, and we said, hey, don't worry, we're only going to have polynomials in the top and the bottom. It technically could get really nasty with square roots and ln's and e to the power of, but we're just going to have polynomial tops with polynomial bottoms. We talked about domain. Whenever you have a denominator, he can't be who? Zero. So we have these things called discontinuities. Then we said, hey, you know what? They have names based on how they act. They have names based on how they occur. When I say removable, what should removable make you think of? Holes. And why are they called removable? Remove it, right? For some reason, it doesn't connect to some people. But holes, removable, you can factor and cancel. So how you guys say it, I would say technically reduce. Because canceling is like 5 minus 5 is 0. Reduce is 5 over 5 is 1. See what I'm seeing? Why I'm using reduce instead? So when it goes away, you have a 1 left. Anyway. Holes can be reduced out. And we said there was a quick clue. You can take your discontinuity, and if it's like a nasty polynomial on top and you're not exactly sure how to factor it, you can plug in real quick and say, hey, what happens? Is the top 0 also? And if it is, there's a clue that they are able to be factored and canceled. Reduced. Now I'm using it. Vertical asymptotes, non-removable. Why? Because they can't cancel out. Why not? I see 2's, I see x's, I see pluses. What's illegal about what I was just saying? All of it. You can only reduce when, remember my trick yesterday? You have to see numerators and denominators as being grouped. They are quantities. There's a sum. That's a sum. It's a whole thing. A binomial and a binomial, since they do not match, you cannot reduce anything. Poor little kittens that keep getting killed. So then we say the discontinuity is a vertical asymptote. And the hint, if you plug in, he doesn't look like a hole. He has a number over 0. That's just a quick little hint to make it so you can see him. Now, how was I able to graph this line yesterday? That's super hard. How was I able to make him look pretty? What's C the same as? Why is this so much easier to graph? Y equals mx plus b is the line. So I was able to say b is -1. Oh, got it. M is 1 over 1. Oh, got it. Up 1 over 1, up 1 over 1. But what on earth did I do? There. And why? It's a hole because at -1, the point that should be there at -1 is not. If we want to see exactly where that point is, we can say, you know what? These two are the exact same. I just have to state the discontinuity because he wouldn't have it otherwise. So you can plug in the -1, you get -2, you know exactly where to put that little hole in. You're done. Now, what was I able to graph down here? Is there very much going on? I have a vertical asymptote at -2. I cheated and I put a horizontal asymptote at +2. We'll see that and review why that's true today. But what's going on as you come towards, with a function, as you come towards a vertical asymptote? What's going on? Do you hit it? No. Do you pass it? No. What do? You skim it. You can skim it this way. How else can you skim it? This way. You can skim it that way, or you can skim it that way, right? There are only 4 options for what can happen. We were just starting to talk about those 4 options yesterday. We were saying, hey, in order to help us with this whole thing of getting graphs of rational functions, if we have a vertical asymptote, we have to kind of figure out what's going on around the vertical asymptote, and we were saying there are only 4 options for what can happen. Either they come and skim together, imagine that's a little bit more that way. Together up, together down, opposite. One up, one down, opposite the other way, one down, one up. But how do we know the difference? You got your graphing calculator. We're going to start there. We're going to start with the graphing calculator. Then we're going to put that away and say, okay, can we do it without? Go ahead and get the graphing calculator. I want you to put in your y1, -3 over x plus 1. Remember, if you're dividing and you're not using that cool little fraction, do you guys remember what the cool little fraction button is? It makes it pretty. Alpha. Alpha y equals. There's the green one with the y equals. Math has like changed a decimal to a fraction, but alpha y equals enter. Gives you a nice little top bottom. Alpha y equals enter gives you a nice little fraction. If you don't have an old calculator, sorry. But if you're doing it the old-fashioned way, you could say -3 divided by parentheses x plus 1, the quantity x plus 1. Okay. You have them in your y1. Before we go any further, what is the domain? Good. X cannot be -1. And would you say that at -1, there's a vertical asymptote and a hole, and why? Don't just tell me and guess based on the page that we're on. Which one? Why? You can't factor it out. You can't simplify. You can't reduce. Right? So, the other way you could check it, yeah, you could plug in and you could say, hey, what happens when you plug in -3 over -1 plus 1 is, oh, that's a vertical asymptote. That's a trick, and it works every time. So we can say, not only does the domain say -1 doesn't work, but we can say there's a vertical asymptote at -1. There's my negative. Look at 7. Struggle. Sparkboard fail. There's a vertical asymptote at -1. Now, hold on, before we go any further. Where this year have you seen, worked with, practiced, and even been tested on behavior? Please. Behavior. N behavior. Right? Okay. Now with N behavior, what was going on? We were going to the right, and we were going to the left, and we were asking ourselves the question based on the degree of the polynomial and the, what was the other part? The coefficient. Which coefficient were we looking at? Leading coefficient. But wait. What part of it though?
The sign.
The sign. I was looking for the sign. So the sign of the leading coefficient. Okay. Based on the sign of the leading coefficient, we were able to do things like, I don't want to put it up there. It's not in this section. It's the old section. We were answering things like, as x approaches, do you guys remember how we would state snazzily to the right? As x approaches what? Infinity. And we were trying to answer the question, f of x approaches what? Right? And then if we were going to the left, we would say as x approaches -infinity, f of x approaches what? Right? We were trying to answer those questions. We had this snazzy way of writing it. Okay. We're going to use that here, except we're not going, look, we're not going to the right and to the left. Look. we're coming from the right and from the left, in towards one vertical line, one vertical asymptote. So we have to change how we write it. We're not going to the right, to the left. We're coming in from the right and from the left. So here's how we're going to write it. We'll get back to how to do this in your calculator in just a second. Hold on. In your notes, I want you to write the following. We're trying to answer the questions as x approaches. You guys notice in those pictures, we're trying to describe as we come from the right and from the left of -1, of the vertical asymptote, whoever he is. And in this example, he's -1. But the confusing thing is, how can I symbolically, with notation, describe the difference between these two? Aren't they both coming to -1? So how do I say that one is from the right? Oops, no, let's do from the left. That's what my first table was. From the left and from the right of the vertical asymptote. I mean, if you put words there, yeah, I guess you can say that there are two different approaches. How can we symbolically, with notation, show the difference? Because right now, where's my marker? There it is. These are talking about two very different things, and we'll talk about these in a second as to what exactly is going on. But how do I show the difference? Can I squeeze them in? I'm quite. Try and E for effort. Let's just move them back. Okay. Here's how we show it. We have to keep -1, -1, because it is the vertical asymptote, but what we can do, and what is commonly practiced in math, especially as you get into pre-calculus and calculus, is to put something little in the power that denotes how we're coming. And specifically, I don't like my plus sign. If we're coming from the right, we're coming from numbers a little bit more than, and we put a plus. If we're coming from the left, we're coming from numbers a little bit less than, and we put a minus. It's literally in the exponent, the superscript spot, but it doesn't mean a power. And it doesn't mean a sign like -1 becomes +1. It just means -1 from the left and -1 from the right. Now, looking at these two little things from your graphing calculator, first of all, how can we make our graphing calculator do this? Like not go by a set increment, but go by exactly what we ask it to do. Okay, go to your window, table 7. Second window, right? And go ahead, you can make the table start 0 if you want, that's pretty typical, but it's not going to make a difference. You just need to change the independent to ask. Remember that one, kind of, in the handbook? Make it ask. Now you should have the function already in your y1. If you don't have -3 over x plus 1, you're in some trouble. But then you can go to your second table. Now, if it still has stuff from the beginning of the year, there are numbers already plugged in. How do you clear it? Not clear, sadly. Delete, delete, delete each of the entries. Delete, delete, delete each of the entries. If there's anything in there. And if there's not anything in there, I want you to go ahead and start putting in and see if you agree. 0.5, 0.9, ooh. -0.5, -0.9, -0.9. While you do that, let me see if I can make my notes look prettier. An error is not necessarily bad. It depends on what you're plugging in. Should the function work at -1? No. Wait. Did they plug in -1? Nope. But your calculator can only fit in so many digits. They put in, look, they did not, it's selected. They didn't put in -1. They put in negative 0.99999. Anyway, negative 0.999. Okay? But what the calculator have to do to fit it in, it rounded. So it shows negative 1, but it's not truly negative 1 because. And what does E5 mean again? Scientific notation times 10 to the power of 5, which means move the decimal place to the right 5, which would be 3 and 1, 2, 3, 4, 5. Nope. Yeah. 1, 2, 3, 4, 5. Oh, they added an extra number. What's negative? Yes. You got lost. Question. If we know that the answer to each of these blanks is either a positive infinity or a negative infinity, what would you answer based on this table? As you get closer and closer and closer and closer to negative 1, isn't it going down and down and down and down? And the answer would be, I agree. As we come towards the vertical asymptote, it's either going up or it's going down. And this one, going down. But wait, do the numbers even really matter then? If we know it's one of the infinities, what's the most important thing we need to know? If we know it's one of the infinities, all we need to know is it positive or is it negative? Is it going down or going up? We're going to use that clue in a second. But over here in this table, now some of you might be like, hold on, wait, from the right, from the left, what? Negative numbers are a little hard to do this with. But if you think about a number line, if you think about negative 1, Question, where's negative a half? Where's negative 0.9? Can't show this one. Negative 0.999. Where are those numbers coming from? The right. And if you think about negative 2, negative 1.1, oh man, we jumped in. Quick! Negative 1.01, negative 1.001, negative 1, that's from the left. Okay, so that's what I'm talking about. And as you plug in each of those, guess what? Is he really negative 1?
No.
What is he? I think it's one more zero. They added 2 zeros? Yeah. No, just one. Okay. Just a quick heads up. Because at negative 1, it doesn't exist, and we know that there's a vertical asymptote. We don't even care about the numbers, we care about the signs. Kiddos, where's this one going? Which means positive infinity. Which means positive infinity. If you want, check out your graph really quickly. Does this make sense based on what the graph looks like after the graph?
Where do you get the numbers for the tables?
To be honest, to some extent, it's off top of your head, which I'm training. To say if we're coming negative 1 positive, don't start far removed. I'll show you why in a second. Don't start far removed. Zoom in real quick and still can going really close. So hence the negative 0.9, 0.99, 0.99, etc. And then if I'm coming from the other side, same thing. You started kind of removed on each of them, but zoom in quick. Negative 1.1, negative 1.0, etc. So think about the number line. Think about what kinds of numbers are right on the right and right on the left, and then zoom in quick. That's what we're basically doing. There's no magic in the numbers, besides the fact we're getting closer and closer and closer. If you were to choose like negative 0.8 and negative 0.88, negative 0.888, well, you're still kind of always at least a 10 off. But you're still kind of getting closer. You'll still see lots of negative numbers. You could still make the same call. When you guys look at the graph, your vertical asymptote is at, what was it, negative 2? Negative 1. Did you see from the right the graph going down and from the left the graph going up? Did you see it? Oh, okay. You kind of know what's going on now, right? But what do we have to use to do this? Calculator. Okay, calculator's off and closed and down. Off and close and down. What if no calculator? There's a way to do it without your calculator, but the decimals were awful. And the numbers were huge. Don't worry. To be honest, I think this is so much easier than the whole process of your function going to your table and zooming in. Let me show. We're still answering two questions from the left and from the right. You guys notice the example has not changed. We already know the answers we're supposed to get. We're just trying to see, can we do it without a calculator? From the left, x is coming towards that -1. Remember, we have a vertical asymptote at x equals -1. From the left, it's -1. Wait, left of the number line lower than -1. Okay, below minus. We're still trying to figure out how do we answer the question. Where are the heights going? From the right, as x approaches -1, from the right on the number line, number's a little bit more positive than. And f of x is approaching. Austin, go ahead.
Wait, why is there no horizontal asymptote?
There actually is a horizontal asymptote, and it's at y equals 0, but we'll get back to it. Right now, we're just checking the behavior around the vertical asymptote, so hold on. But vertical asymptote is at x equals -1 because it comes out of the denominator and it can't be canceled. It's not a whole. Okay, here's the dealio. On the page before, we made these huge tables. But actually, at the end of the day, we actually answered, wait, we knew it was infinity. We just needed the positive or the negative. Guess what? You don't need any of those numbers. But what you do need to do, what you do need to do is the following. Just pick one and check the sign. So with math, literally, you pick a test value, pick one, check the sign. Pick one what? Well, let me show you. Thinking about our number line again, right? There's -1, there's 0, there's -2. If I'm coming from the left and zooming in real close, what's something real close to -1 on the left? -1.1. Is that? I know. No. It's okay. Negatives. Our brain always is like on the left. It's lower. It's more negative. So on the left, we're going to choose -1.1. Actually, it could be -1.01, -1.2, something close. What's something on the right? 0.09 is way over here. Still over here.
-0.9.
Exactly. See it? 0.9 gets that way. 0.09 comes towards 0. Just pick one each. And here's what we're going to do. We're going to take him, who is the function. We're going to take him, who is the function, right? -3 over some x plus 1, which just means value plus 1. We're going to input from the left our -1.1, and we're going to input from the right -0.9. And we're going to check the sign. For each one, for each direction, plug one in, plug one test value, zoomed in real close, one on one side, one on the other. Don't worry about the number. Check the sign. Meaning, ready? What sign is -3 you're going to keep on having? Negative. Over. What sign is -1.1 plus 1, or -1.2 plus 1, or -1.01 plus 1? That's why I could have chosen anything. All of them plus 1 is a negative. Oh my goodness, well, every negative over every negative is going to be a positive. Guess what I'm going to choose? Positive infinity. Hey, no table, no plugging in, no crazy numbers needing to approach. So you guys try to check the sign on the bottom one while I answer a question. David.
Why'd you choose -1.1?
I needed something on the left, and my advice was zoom in real close. Zoom in real close. It could have been negative 1.2, could have been negative 1.01. Something that's a little bit more negative than negative 1, but still not too far away. That makes sense. So what you guys get? Oh, sorry, do you have a question?
Why did you want to choose like -2 or 0?
Here's the quick reason why. As insert a blank page to delete it later. Some functions might have a vertical asymptote at -1. And they might actually do this sort of thing instead. So if I don't get in really close to the vertical asymptote, I might be somewhere, let's say it shows -3 or -4, etc. It would show a positive, and that's not true to what's going on. So I need to get in real close. Remember, vertical asymptotes, the function gets in closer and closer and closer. If I'm like 0.1, 0.01 away, oh man, I can see exactly what's going on. Does that make sense? And it can't go too far away because maybe it's somewhere else because it's doing its own little who knows what over here, right? Okay, let's just delete this whole thing. Delete. Don't see it. There. Okay. Did you guys already check the sign of the next one? What'd you get? On top. Work it out. That is that. On top, -3 is going to stay negative no matter what, so no big deal. Negative on top. On bottom, -0.9 plus 1, -0.8 plus 1, -0.99 plus 1. Anything you chose close to -1 is going to still be a positive. And a negative over a positive is a negative. So hence my answer is done. And from those we can say, oh, sweet. So, -1, coming from the left, somehow it's going to be like, burp, burp. No, coming from the left, where does it go? I switched it, sorry. And coming from the right, somehow it's going to go, and Caleb, if you notice, I'm not showing a lot over here because I don't know exactly what's going on. Unless, Austin, we figure out the horizontal asymptote and we know exactly where it's going as it goes to the right and to the left. Okay? Whew. What is this whole shabam? Behavior where? Near vertical asymptotes. Not ends, but near. Okay. But we just talked about, oh, how nice it would be. Oh, come on. We just talked about how nice it would be to finish the graph to know exactly what the horizontal asymptote is. I know. See, I was thinking about that. Austin, thanks for helping out. So, horizontal. Horizontal. Now, here's the crazy thing. Horizontal asymptotes do not come from denominators. From denominators, we find discontinuities which show us holes and vertical asymptotes. Horizontal come from degrees and degree testing. The name of the game is who wins. The end. We do not yet see all things correctly in subjection, but one day we will. However, I won't say who, I'll stop personifying things. I'll say which wins. What wins? Numerator or denominator? Top or bottom? It depends. Sometimes the top will win, sometimes the bottom will win. Wait, what are we testing? How do they win? Right? That's a huge important question. Compare, what did I say? Degrees. We'll get back to the blanks in just a second. Compare the degrees. All right, we're going to get back to exactly the rules of the contest and which one wins and what that means. But let's start back at the very top. Who or what is a horizontal asymptote? Vertical. one x value. The graph as it comes in shoots up or shoots down, and it could behave different ways, but somehow it gets closer and closer and closer and closer on this one x value without ever hitting horizontal asymptotes. How does it get closer and closer? Uh-oh, is there another typo? Wait, I like them. There's no typos. You guys do it. Messing with me. Come back. As I get, or how do I get closer and closer to a horizontal asymptote? To the right, to the left. So, somehow a function to the right is getting closer and closer and closer and closer, and to the left is getting closer and closer and closer and closer. And usually, for all the examples we're going to see, to the right and to the left will agree. Sadly, in calculus, there are some harder ones where actually to the right is one way, to the left is another way, and it's a little bit rough. But for us, to the right to the left will agree. These are like the basic functions that we're looking at. To the right to the left will agree. But question. Are the f of x's going to infinity or negative infinity if there's a horizontal asymptote? This was going to infinity, right? That was going to infinity. That and that was going to infinity. So what's this getting closer and closer to? A number. A point, kind of. A y value. The y's are getting closer and closer to, I'm going to call it L. It's actually called like a limiting factor. L for limit. Super snazzy, like calculus term. Don't worry, we're not going any further than that today. But L, the function is going to get closer and closer to a number. What number? It depends on the function. If there is a horizontal asymptote, the horizontal asymptote is going to be at a constant that the y's get closer and closer to. So as x goes to infinity, it's going to the right. Or as x goes to negative infinity, it's going to the left. It is end behavior, but it's not like polynomials that were going like different infinities. Instead, it's coming in closer and closer to a number. And just a quick heads up, if we're talking about polynomials, what do polynomials want to do? As you go to the right to the left, where do they want to go? Up or down, right? They want to go forever up or forever down. So what is going to keep them, aka the tops or the numerators, the normal polynomials, what's going to keep them from doing what they want? The denominators. Right? The top is the polynomial. But as soon as the top gets divided, that bottom could restrict him and could pull him down. Depending on the denominator. If the denominator is really strong, it can pull him all the way down to a number. And if he's really, really strong, it can pull him all the way down to 0. Pull him back, right? But if the top is strong enough, he'll be able to keep going for his potential, right? There's a life lesson in there somewhere. Look deep. But come back. For right now. Polynomials want to be doing whatever, right? The denominators could be dividing and pulling them down. We have to basically do this whole test and say, all right, who wins, who's strongest, who gets their way. The denominators pulling it down, or the numerators trying to soar or dive. Either way. It's not good for life lessons. But anyway, coming back. If the degree of the top is higher than the degree of the bottom, who gets his way? The top. He's going to be going. And if he's going, is he getting closer and closer to anything? No. Hence, no horizontal asymptote. And specifically, it is because f of x, if the top wins, it's behaving like a normal, good old polynomial. F of x is either approaching infinity or negative infinity. It's not being held down. It's going for it. And even though it has a denominator, the denominator is not going to affect it to a great degree. Okay, so if the top wins, he's just doing what polynomials do. He's going. No horizontal asymptote. Number 2, what if the bottom wins? If he wins, he's pulling them all the way down. And all the way down, meaning pulling this one up and pulling that one down. He's pulling them all the way to a whole lot of nothing. keep on going on and on and on and on. That bottom keeps dividing, eating away, pulling it down to zero. Could be pulling it up, but either way. Horizontal at y equals 0, which means the answer to my question as x goes to infinity or negative infinity would be f of x is approaching 0. Now, the struggle is, what if they tie? Now, if they tie in degrees, it doesn't mean they perfectly tie like they're the exact same thing. It just means their strength is the same. But they still have these things called coefficients. If they tie, the top is still being limited. But he's not being limited all the way down to 0. Instead, he's being limited to the ratio depends of, can you guys finish that statement?
Always talked about degrees.
Leading coefficients. The degrees are what tell us whether or not there's a tie. The degrees are what tell us whether or not there's a tie. The leading coefficients are what can give us an answer. So, which ones have a horizontal asymptote? Just case 2 and case 3. Which case is not case 1. Technically, there's calculus behind all of this as to why this is what it is, but for right now, we just get to go ahead and use these tests and figure it out on our own. So, examples, you ready?
Yeah.
On the following page, I have 3 examples. We're just going to look at them one at a time, all together. We're going to ask ourselves the question, based on the degrees, meaning, right, the highest exponent, the highest exponential power, we'll say the highest exponent of x. Based on the degrees, who wins? Top wins, none. Bottom wins, 0. If there's a tie, it's a number. Ready? Who? Nothing. Who wins? Write it down. Write it down. The function is 5 minus x squared all over 33x. Oh, there's a 33 in the bottom. He wins. No, he doesn't. We don't look at the coefficients. We look at the degrees. And the top has a degree of 0, block 2. Oh! Look at the highest. In essence, he's a quadratic. In essence, he's a linear. Top wins. So, top is doing what the top wants to do, basically, eventually. So, no more about that. He might be limited for a time, but as you go to the right to the left, the top takes over. He keeps on doing what polynomials do. In this case, that would be a this eventually, right? Next one. Who wins? Bottom. Top doesn't even have an X. He's out of the running right away.
Yep.
Bottom wins. Uh-oh. Bottom wins? He's pulling them down, pulling them down, pulling them down. Where's he going? Down. And down means kind of up and down. Where's he pulling them to? Yep. Whole lot of nothing. Isn't that? Even that problem could be said. Last one. Who wins? They're tied! Hey, he was the one I talked about earlier. And I think I told you the horizontal asymptote. Let's see if we remember why. He's tied because his highest degree terms have the exact same power of 1. So where is their tie? There's a horizontal asymptote. Yeah, the top is being limited, but not all the way to 0. All the way to 2. Ratio of the leading coefficients, 2 over 1 is. You kind of remember him from last year? Where do we find vertical asymptotes? In the denominator. In any denominators where the factors don't cancel out. Those would be holes. Where do we find horizontal asymptotes? Degree tests. That's why it gets hard, because they're both asymptotes, but they're very different ones, and they come from very different places. Something to study, practice, and make sure we have down. Let's keep going. What? Hold on, come back. Pause. This is the end. We're done after that. See? Oh, let's do him first. He's easier. Let's do a slanty one. Technically, this last one, guys, is kind of just of a, let's see what we can do based on everything we've learned. So let's learn about the slanty ones first. Then we'll see if we can put it all together and do something pretty cool. Slanty ones. Okay, slant. Asymptote is technically the nice pithy term is oblique. You might not have known that there could be slanting asymptotes. If you want to take a quick second, after writing oblique, put that example on your calculator and check out the graph and be like, what on earth is a slanting asymptote? As soon as you write the first part, if you want, go to your calculator real quick and be like, wait, what is this? What is this? What is keyword? Then I'll show you how to get it. There's a little occurs when, just so we know when to be on the lookout for him. That'll help us know when to look for oblique asymptotes, because only rarely is there one that will appear. But it can happen. But it only happens when the degree of the numerator is higher. I need to actually add one thing. I need to add one little thing in there, but you guys keep writing for a couple seconds more. You want to throw this function into your calculator and see what on earth a slanty asymptote is. But first, I need to add one quick thing in. Ready? Hold on, everybody. Is higher. Wait, it's not just any higher. It's only higher by 1. Only higher by 1. So it's not a lot higher in terms of degrees. It's only higher by 1. So you guys check out the graph and see what he looks like? What is a slanty asymptote? It's literally a slanty asymptote. See? He's not vertically, he's not horizontally, he's slanted. Oblique, whatever. Slant. Slanty form. Okay, but hold on, wait a minute. Isn't it still a line? Well, if it's still a line, shouldn't it still look like a line? But how can we get a line? It's a quadratic up top, it's a single down bottom. If we divide, we'll take out that one, and we'll get whatever's left. So, yes we do. With long, you guys wrote that, didn't you? Here, I thought you were amazing. Just kidding, you are. Okay, so coming back. Long division. How do we find the slanty asymptote? How do we find who he actually is so we can actually express him? We say, hey, top drops, right? I guess it could be synthetic, but just in case it's a little bit worse, so you can't do synthetic, let's do long division. It's the safest one. It always works. We have our x, we have our x squared, we have our minus x. We're doing division like snazzy, nicely trained algebraically students would. Switching all of our signs, getting rid of him. We have a remainder of, gross. Just a hint. If there's a slanted asymptote, there's always a remainder. That we focus, always ignore. And we say there's an oblique asymptote, or if you want to make it SA, I don't know, I suppose we could, at y equals, just take the answer, ignore the remainder, x. And let's test our theory by going in our calculator and saying, hey, if we graph y equals x, are we going to actually see what it's skimming? I think so. Go team. Do you see him get in there? Nice. If there is a slanted asymptote, one quick other thing for us to note. Guys, if the top's higher, if there's an oblique one, if there's a slanted one, the top is higher. There is no horizontal. It's kind of like in lieu of, in the place of. Packing up already, guys. You already saw there's no more example. Okay. Pause.
No, that's not right.
but it's only gonna happen if the top is greater by 1. If it's greater by 2 or 3 or 4, because x cubed over x equals 1. Alright guys, hold on. What if you see in homework, something that says factor and reduce? Can you do it?
Yes.
Y-intercept, plug in x is 0. Can you do it?
Yeah.
Plug in y is equal to 0 and solve it.
Yeah.
Find a vertical asymptote. Find a horizontal asymptote. They could say something, hold on, like, stop mathematically dancing, like, go find us extra points. I actually don't want you to do that. Instead of the extra points, ready?
Yeah.
I want you to check, uh-oh, what am I going to say?
Behavior.
Just like we did today in class. Don't go finding a table of all these extra random points.
Hello.
Check the behavior and it'll be enough. I told you guys work with this before, even if you're not here Monday, Tuesday, you are here, maybe you should specialize.
Surprisingly, I'm the last one with a different pattern.
You're what?
I'm the last one with a different pattern. Because usually Tyler and I are the last one.
Yeah, that is true. I will book it out of here. Do you have some homework to do? Do you have some homework to finish up? Something.
Or just really dislikes me. Have a magical weekend, to do it.
Thanks, you too, bud. See you later, Caitlin. Hey, Kayla.